All right, so the last thing I want to talk about here in chapter 19 in this last unit is what's called acid and base dissociation constants, okay? So what this basically means is when an acid and a base dissociate or break down in water, okay? So we can use generic formulas, meaning it happens with any acid or base. So we can just use, for example, this formula, okay? So acid dissociation constant, I'm going to do the first here for the acid and then I'll break down at the base, but Ka. Ka is what's our acid dissociation constant. And notice my generic formula, Ha. Whatever that A variable is, it could be Cl, it could be F, it could be NO3, whatever it is, it's just an acid. It could be hydrochloric, it could be hydrofluoric, it could be nitric, whatever. I will say this, that Ha would be considered a monoprotic acid. Monoprotic means just the one H. H2SO4 is a diprotic acid, okay? But HA, 1H, monoprotic acid. So here's the generic formula for a monoprotic acid. HA, notice with water, if you remember from the beginning of the unit, H gets donated to the H2O, and we get that H3O plus the hydronium ion, and then whatever the A is. So here's the generic formula. Now, in order to solve for the Ka, the K is the concentration of the products multiplied together. All right, concentration of the products over the concentration of the reactants. Okay, now we do have a concentration of H3O plus and the A minus. So those are going to be multiplied together. I know it says plus here, but when you multiply, when you want to solve for the Ka, you multiply them. So the Ka is the H3O plus ion concentration times the A minus concentration, all right, over the reactants. Now here's the wrinkle. It's just the HA that we're talking about. It's just the HA because this is water and there is no concentration for that. So we ignore the water. So it's just the concentration of the H3O plus ion concentration, which is what's called the equilibrium concentration of H3O plus, multiplying it by the A minus. All right? So that's how you determine and that's how you solve for the Ka. I'm going to erase this again and write it again. It's the Ka is the H3O plus ion concentration times the A minus concentration over the HA. Okay? We ignore the water. The HA is the initial concentration of the acid. Makes sense, right? Because it's the acid and we're putting it into water, or we're putting water into it. You should always add acid to water, but you're putting the acid into the water, so that's the initial concentration. This is the equilibrium concentration. Now here's the little wrinkle. Notice the coefficients for this. It's a generic formula, but the coefficients will always remain the same. They're both 1. Since the coefficients are the same on this equilibrium concentration H3O plus, then that means the value is the same. Meaning, whatever the H3O plus ion concentration is, this one is the same, the A. So I only have to give you one. All right? So if you had a problem, what did I have? Let's say 4.2 times 10 to the minus 3. All right? Where I said the H3O plus ion concentration is 4.2 times 10 to the minus 3 molar, and the initial acid concentration is 0.1 molar, you would plug it into this as Ka equals 4.2 times 10 to the minus 3 times 4.2 times 10 to the minus 3. Of course, you could just square it over 0.1. When you solve that, I get 1.76 times 10 to the negative 4. Okay? There's your acid dissociation constant for this acid. You know, it could be anything. Could be formic acid. Could be cyanic acid. You don't have to know the formula. You just need to plug them in. The equilibrium times itself over the initial. All right? So let me erase this and very quickly, I don't want to waste your time, talk about the base. The base, same exact thing. The base here, let me grab a different color, is going to be the OH minus concentration. Notice I used a generic base, whatever that base is. OH minus times the HB plus over the initial concentration. Again, the B is the initial concentration, and then these, of course, are your equilibrium concentrations. And they also are always the same. All right? So, simple enough. Take that equilibrium concentration, multiply it by itself, square it, and then divide by the initial, and that's how you solve for acid-base dissociation constants.